A buffer solution is defined as an aqueous solution that resists a change in pH when a small amount of acid, base, or water is added to it. Buffers can have either an acidic, a neutral, or a basic pH, and they are made up of a mixture of a conjugate acid-base pair. The two types of buffers we're going to talk about are acidic and basic buffers. To start with, acidic buffers are buffers that have a pH less than 7. The way that these are made is by mixing an aqueous solution of a weak acid with a solution of a salt containing a cation of a strong base and the anion from the weak acid. An example would be ethanoic acid and sodium ethanoate. Ethanoic acid is our weak acid. Sodium ethanoate is the salt that contains the anion from the weak acid and a cation from a strong base. This would form the following equilibrium. So the way that buffers work is they resist changes to added amounts of acid or base. If an acid was added to the system, in effect, we're increasing the H3O plus concentration. According to Le Chatelier's principle then, if we're increasing the concentration of a product, our equilibrium is going to shift towards the left, and then we'll effectively decrease that H3O plus concentration back down to where we began for our buffer. So it resists that change in pH or the change in hydronium ion concentration by shifting the equilibrium in the opposite direction. If a base is added, what we're doing is we're increasing OH minus concentration. Now, because we know that the OH minus concentration is related to the hydronium ion concentration, if we increase the OH minus, effectively we're decreasing the H3O plus concentration. In this case, to replenish the H3O plus that's being decreased, the equilibrium is going to shift to the right in order to restore the H3O plus concentration and therefore resist a change in pH. Alkaline buffers or basic buffers are those that have a pH greater than 7. They are made by mixing an aqueous solution of a weak base with a salt containing an anion of a strong acid and the cation of the weak base. An example would be ammonia and ammonium chloride. So ammonia being our weak base, ammonium chloride, we have the salt from a weak base, the cation from a weak base, and we have the anion from a strong acid. Now it would form this equilibrium here. Similar to acidic buffers, these are going to resist changes to added amounts of acid or base. So if we add acid, we're increasing H3O plus. Effectively, we're decreasing the OH minus concentration. So in order to restore the OH minus concentration, our equilibrium is going to shift to the right, and that will then maintain the pH of the solution. If base is added, we're increasing OH minus concentration, so our equilibrium would shift to the left, and therefore, again, restore the pH of our system. We can do calculations to figure out the pH of a buffer if we're given the concentrations of our acid or base along with its salt. There are two assumptions that we're going to make with buffers, is that the initial concentration of our acid or our base, in this case our acid here, CH COOH. So the initial concentration is not going to be much different than the concentration we reach at equilibrium, because it's resisting those changes. Also, the second assumption we're making is that the concentration of our salt initially is also about the same as what it's going to be at equilibrium. Again, because we resist those changes when we add acid or base. So if we were to take this problem, set up an ice table, initially we have 0.50 moles per decimeter cubed of our acid. Initially we have 0 hydronium, and then we would have 0.25 moles per decimeter cubed of our CH COO minus. Because we've got 0 hydronium, the change is going to be positive for that. So it'd be positive for this guy, negative for this guy. But we know that this one and this one are negligible. And that's because of the two assumptions we've made here. So our equilibrium then is 0.5 and X and 0.25. So we can set up our Ka. Our Ka is going to be our H3O plus times our CH3 COO minus divided by the CH3 COOH. Now I'm just going to put the values in here. And we're given our Ka. So it's 1.8 times 10 to the negative 5. Okay. If we solve for this, we would get an X of 3.6 times 10 to the minus 5. And remember, X is our hydronium ion concentration. To get pH then, we're going to take the negative log of our X value, and that would give us a pH of 4.44. Now there is an easier way to do these calculations, and that's using the Henderson-Hasselbach equation. And that is given here, where the pH is equal to the pKa plus the log of the salt, concentration of the salt divided by the concentration of the acid. This provides a shortcut for buffer calculations when the Ka value is small. For basic buffer solutions, there's a similar one, except this is going to be POH is equal to PKB plus the log of the concentration of the salt divided by the concentration of the base. In this example here then, we've got a weak acid and we've got the salt containing the anion of that weak acid. So what we need to do, using the Henderson-Hasselbach equation, we're going to solve for the pH. So it's pKa plus the log of the salt divided by the acid. It's important to identify which one is the salt and which one's the acid so that we use this equation correctly. So the sodium lactate is our salt, the lactic acid is our acid. We're going to plug in our values then. pKa is the negative log of our Ka, which is 1.4 times 10 to the minus 4, plus the log of our salt concentration, 0.25, divided by our acid concentration, which is 0.5. So if we were to solve this, we would get a pH of 3.37.